ladies and gentlemen, boys and girls. If you like superheroes and can tolerate a side of physics to go along with it, then you are in the right place. Transparent Physics is proud to present another exciting episode of Action Physics. The goal of Action Physics is to take a look at the world of superheroes through the lens of introductory physics. You don't need to know any physics going in. I'll try to teach you the basics of what you need to know as we go. Today's episode is titled Quicksilver, The Touch of Death. And we're going to be focusing on some events from the movie X-Men Days of Future Past. Just a real quick background on the movie before we get into the details. X-Men Days of Future Past was released in 2014 as part of 20th Century Fox's sort of X-Men cinematic universe. They released a lot of movies, and not all of them were very good, but X-Men Days of Future Past, I think, was definitely one of the better ones. It is set in 1973. The plot is that JFK has been assassinated. Magneto, the magnetism master mutant, has been implicated in the assassination, and he's currently being held in a special metal-free prison that is buried deep beneath the Pentagon. And as a result of this turning of events, there's sort of a historical set of footprints that lead from there to a dark future where giant robots, sentinels, have hunted mutants to nearly extinction, and the world itself's a pretty bad place, whether you're human or a mutant in general. So there is a small band of surviving mutants, and a plan is hatched to send someone's consciousness back to the past, where they can try to avoid the events that led up to sort of the apocalypse that they are currently living in. Wolverine is chosen for the task, so his consciousness is sent back into his younger body, where his goal is to meet up with some other mutants at the time and break Magneto out of prison. He works with a younger Charles Xavier, who we know as Professor X. In this particular movie, he's sort of traded his mental powers for the ability to walk, and he's also working with Quicksilver. Quicksilver is just a mutant that can run super fast and do things super fast. So they all team up to break Magneto out of prison. And as the four mutants are making their way out of the Pentagon, they enter a kitchen area where they encounter a squad of security. Security immediately pulls their guns. Magneto is getting ready to send some knives flying through the air at them. The guards all fire at the assembled mutants. And at this moment, Quicksilver springs into action and manages to disable all the guards and save his friends from being riddled with bullets. I think sometimes some movies are defined by like one scene that just everybody remembers that scene from that particular movie. I think the Quicksilver fight scene is the scene for X-Men Days of Future Past. It is just so well done. I saw it back in the theaters when it was released initially, and it just blew me away when I watched it. And even now, watching it all these years later, there's still details that I didn't notice before, like when Quicksilver's running around the wall at the start of the scene. The tiles are shattering under his feet. Just lots of fun details they snuck in there. Plus, while this giant fight scene's going on in slow motion, they're playing Time in a Bottle by Jim Croce, which is a great song, and it's such a good juxtaposition to everything going on screen. Plus, fun fact, Time in a Bottle was released in November 1973, which is the same year the movie was set. So nice job, background researcher. All right, then, time to get down to business. Action Physics wants to know, can Quicksilver safely dispatch all those guards without seriously injuring them? In the movie, it just looks like he knocks them all out. They all fly around to the ground and get knocked out, and then Quicksilver and his friends sort of leave the kitchen. Is that possible? Can Quicksilver disable all those people in such a short period of time without causing serious injury? Well, in order to answer that question, let's turn to Newton's second law of motion. All right, Newton's second law is part of a series of three laws that are called Newton's laws of motion. And what they do is explore the impact of forces on masses and how those cause objects to move or not move, or change their motion or not change their motion. And the second law states that objects will accelerate in the direction of the unbalanced force. And there's a little bit to unpack there if you haven't had the background yet in the physics. Acceleration, a lot of times when people think of acceleration, they think acceleration just means speed up. But from a physics perspective, it means basically to change your motion. So you could speed up when you accelerate, you could slow down when you accelerate, you can even change your motion. You could be going forward and then turn to the left. That's also considered acceleration. So in the context of what we're talking about, when I say the word acceleration from here on out, it doesn't mean that it has to be speeding up. Acceleration just means the motion is changing somehow. And then a force is a push or a pull. And when we're talking about an unbalanced force, that basically means the force is winning. If you were to push on something and it pushed back on you with an opposite force, the object wouldn't move. Or let's say a tug of war and both sides are pulling with an equal amount of force, again, the object's not going to change its motion. So what we're looking at is a force that either is unchallenged or it wins against the force that is opposing it. Now, all that can be summarized in an equation because physics is pretty cool like that. So we have the expression F net equals ma. F net refers to like all the forces added together. M is the mass of the object, and then A is the acceleration. And the acceleration's in green because that's kind of like the big thing in here, because Quicksilver definitely changes the motion of a lot of objects during this clip. And let's take a look at that in a little more detail. And the specific aspect of acceleration that we're going to be looking at is the idea that deals with a change in velocity over change in time. When you calculate acceleration, acceleration is equal to the change in velocity divided by the change in time. So either of those can result in a large acceleration. If the velocity change is large, you can have a large acceleration. If the time interval over which that occurs is small, that also can result in a large acceleration. If you have something in the denominator that gets smaller, the overall fraction gets bigger. And Quicksilver does things very, very quickly. So as the time interval gets shorter, the acceleration gets larger. You need more acceleration to cause something to change its velocity in a shorter period of time. So we're going to hang our hat sort of on that relationship, and over the next couple slides, we're going to try to figure out the actual time for events that occur in the clip. We're going to use that time to find acceleration, and then we're going to use that acceleration with Newton's second law to estimate the force that Quicksilver is able to exert. All right, then the first thing that we need to do in our analysis is try to get a sense for what kind of time's passing. In the clip, everything's traveling really, really slow, and it's not like there's a clock that's ticking that we can figure out how long things are taking. So we're going to have to infer it from other things going on inside the clip. And you may have heard of the Internet Movie Database. Well, there's also an Internet Movie Firearms Database, and what they do is they look at the firearms used in movie and try to see what kind of stuff's getting put into the different scenes. So they actually have an entry for X-Men Days of Future Past, and the plastic gun or whatever they're made of, the metal-free guns appear to be modeled after Colt Pythons. And Colt Pythons use .357 ammunition, and more internet research leads to the fact that .357 ammunition, let's just make a safe assumption that its muzzle velocity is 550 meters per second as the bullet's fired. All right, the next up we need to look at the movie clip a little more closely, and I picked a scene from the clip where it's a really nice shot where the bullets are kind of streaking across the screen. Nice straight line, couple seconds of time that we can look at them with, and I use that as sort of a sample set for the bullet's motion as everything's slowed down. And I picked a segment of that clip that lasts for almost 4 seconds of quote-unquote movie time. And during that time interval, I made a rough estimation that the bullet traveled what I called 8 bullet lengths during that time interval. And now we have a distance, because if we assume that the bullets are standard .357 bullets, 8 of those bullets lined head to tail would give us a distance of around 32 centimeters or 0.32 meters. All right, we have all the pieces we need to figure out how much time is actually passing during the clip. We're going to start with the kinematics equations. If you haven't had your physics yet, you'll get these equations pretty early on in your studies probably. We have an equation d equals vit plus 1/2 at squared, and it looks kind of complicated, but it simplifies right out to t equals d divided by v. Why is that? Because the acceleration is 0. We're going to assume the bullet doesn't speed up or slow down during that time interval. So the 1/2 at squared term drops out, leaves us with just d equals v times t. Manipulate that to solve for t with some algebra. We already established the displacement of the bullet is around 0.32 meters and that the speed of the bullet is around 550 meters per second. So we know everything on the right side of the equation. We know our d, we know our v, we can solve for t. When you plug that into a calculator, around 32 centimeters of distance would be traversed by a real bullet-ish in 0.00058 seconds. So it does not take very long at all for a bullet to travel 0.32 meters. And in the movie scene, however, it takes almost 4 seconds, 3.78 seconds, I estimated, for the bullet to travel that same distance. So this is kind of our Rosetta Stone. 3.78 seconds is the slowed down movie time, and 0.00058 seconds is the actual time. So we can get a relationship between the two of those, and I'm estimating that each second of quote-unquote slowed down movie time is roughly 1/5 of a millisecond of actual time. And we're going to use that moving forward. Okay, so Quicksilver accelerates many, many, many things during this movie clip. We are going to just continue to focus on the bullets again. Towards the end of the clip, again, there's a series of bullets moving towards the other mutants in the room. Not all of them are going to hit. Quicksilver identifies 4 bullets of concern. 2 of them he nudges out of the way, and 2 of them he actually physically sort of grabs and drags out of the way. And we're going to focus on the 2 that he sort of drags out of the way. We're going to assume that the forward motion stays the same, and he's just moving them to the side. Now again, why he just didn't pull back on the bolts a little bit and just stop them entirely, it's whatever, it's fine. It's still a fun clip no matter what. But we're going to note that sideways velocity that he gives the bullets, that he also removes the sideways velocity. Because to the best of my vision when I watch the clip, when the scene starts up again normal speed, the bullets just continue to fly forward. So it's not like he gives them a big velocity to the left or the right. Otherwise, they could just hit somebody in the side of the head instead of the front of the head. So they still keep moving forward. So he adds velocity left or right, and then he takes that velocity away so that they're still just moving forward with the same speed that they had. And this, combined with our understanding of the time from the earlier section, gives us pretty much what we need to figure out the acceleration. We're going to assume that he moved each bullet by around 20 centimeters of distance to get them out of the way of their targets. And in both bullets' cases, it was about 1 second worth of movie time that it took for him to do that. Because we assume that he's not giving the bullets any sideways velocity. Whatever speed he gave to the bullets to start with, he's got to take away before he lets them go. So just for simplicity's sake, we're going to assume that he's just constantly speeding them up for the first 10 centimeters and then constantly slowing them down for the second 10 centimeters so that when he's done with the 20 centimeters, there's no sideways motion left. It simplifies our analysis. And now it's time to break out the calculator. Hey, look, it's the same equation again, d equals vit plus 1/2 at squared. But in this case, we're going to assume that the initial velocity sideways is 0, so that term drops out. So we get instead d equals 1/2 at squared. We assume that the displacement he's moving them is 10 centimeters. Remember, we're only looking at half of the 20 centimeters. We're just assuming that he's speeding the bullet up sideways over 10 centimeters. And because it takes 1 second of movie time to completely displace the bullet, we're going to take half of that because we're assuming this is the half where he's speeding the bullet up. The half where he slows the bullet down is basically symmetrical in terms of the amount of forces, so we're not going to spend any time investigating that. If you put the d and the t into the equation and solve it for a, you're going to have to do a little algebraic manipulation first. Transparent Physics is happy to help you with that. If you look down through our physics toolbox, I'll show you how to manipulate equations as well. But in any case, moving forward, So when you do the math, the acceleration works out to a very, very large value of 17.8 million meters per second squared. And in comparison, the acceleration of an object when you drop it due to gravity is around 10 meters per second squared. So the bullet experiences a tremendous acceleration. And again, if we're going to be realistic about it, that bullet probably wouldn't survive this. It would probably just like melt in his hands. But whatever, it's a movie, so let's keep going. Okay, then, so we estimated a time. We used the time to figure out an acceleration, and we're going to use the acceleration to figure out a force via Newton's second law. Newton's second law says F equals ma. So we just multiply the mass times the acceleration, see what we get. The acceleration, as noted before, 17.8 million meters per second squared. The mass of a fired 357 bullet we're going to estimate to be 10 grams. But you can't use grams in physics. Generally, we're going to convert it to kilograms, so it'll be 0.010 kilograms. Multiply those two together, and you get a very large number. You get 178,000 newtons, and a newton is just a unit for force. I like to tell my students, if you open the palm of your hand and imagine a reasonably regular apple sitting in the palm of your hand, that's about 1 newton of force, roughly speaking. Maybe a smallerish apple, but that's about a newton. A newton is not very much force. 178,000 newtons is a very large amount of force. Roughly the equivalent of 40,000 pounds of force. And that converts to around 20 tons of force. So, and that's just between Quicksilver's index finger and his thumb. Between the two of those objects, he's able to create 20 tons of force. So this means that like Quicksilver is like strong and stuff. What is 178,000 newtons in some context? Well, I looked some stuff up on the internet, and a golf club hitting a ball is estimated for forces up to 10,000 newtons during impact, and no one wants to get hit by a golf club, that's for sure. Probably another thing you probably don't want to get hit by is a baseball bat. Baseball bat can exert forces up to 40,000 newtons during an impact. And again, these are rough estimates, but it gives you sort of a ballpark figure. And each of these interactions is around a millisecond or so. You may have seen pictures where it shows the golf ball or the baseball, and they're just incredibly deformed during this interaction. Golf balls and baseballs are designed to deform, and then they return back to their shape. So the energy sort of gets stored in the ball, and then the ball returns back to its shape, and the ball sort of flies off in a different direction. And that's all well and good. Golf balls and baseballs can do that. The human body, not so much. So there are some problems with exerting the human body to that much force in such a short period of time, or whether or not it's a short period of time. But definitely it's harder during a short period of time. And the clip is a little bit deceptive. Anytime you watch something in super slow motion, it looks probably a lot more gentle than it is. But these light touches that Quicksilver is exerting on objects are generating tons of force. And it's a massive amount of force that creates a sudden violent acceleration. You can watch a baseball being hit in slow motion, and it might look kind of nice and gentle and sort of like a little bit of ballet and stuff like that. But in the real world, it's a sudden violent crack of interaction. And in addition to that, once an object gets into motion, it's going to stay in motion. So Quicksilver gets these objects into motion, and they're going to keep doing what they were doing. And the movie uses this to some effect. We'll see that moving forward. And this idea of an object continuing to keep the motion that it already has, it relates to Newton's first law of motion, known as the law of inertia. Okay, so I think we have enough pieces of the puzzle now to sort of at least make a back-of-the-envelope estimation for what this means for the guards. And again, I'm not an expert in this field as far as like the physiological effects of massive stress over short time intervals on the human physiology. We're just going to guess. But I'm going to argue it's not going to be good. And we'll take a quick look through all the various interactions that Quicksilver makes during this scene. And I'll give my armchair quarterback of what I really think would be happening to the guards in each of these instances. Remember, in the actual movie, they all just sort of look like they all get punched and they sort of fly around and fall to the ground and get knocked out, and then everybody sort of, the mutants move on. But if this was really happening, and again, that's a strong disclaimer because it is a superhero movie. But if this was really happening, what would actually be happening to the guards? Let's take a look. To the best of my knowledge, none of these guards actually have names. I don't know. I didn't look for their name tags or anything like that. I'm just going to name them alphabetically in the order in which they appear. And we'll start with Agent Alex. Again, the movie clip shows Quicksilver playfully knocking the hat off the back of his head. I want you to imagine instead somebody playfully knocking the hat off the back of his head using like a baseball bat or a golf club. So the idea is wherever there's contact point, he's probably going to have a fractured skull at that point, I would imagine, and his head flies forward, sort of like a reverse whiplash kind of thing. So I'm going to argue with a hyperextension of the neck, probably some damaged vertebrae as his head gets thrown forward by the interaction. Okay, next in the queue is Agent Bradley, and as I was working through this video, I have a tough time sort of deciding who has it the worst from this interaction, but I would say Agent Bradley's probably in the top 3, and he gets a very solid poke in the jaw from Quicksilver. Remember that Quicksilver's fingers can exert 20 tons of force, so I'm hoping Agent Bradley took his photo for his security ID the week before, because I'm going to argue that his jawbone is just going to shatter as the result of this, and also his head's going to get thrown to the left, sort of whipsawed sideways by the force of the impact. So not so great for Agent Bradley. I gotta say, Agent Colin, I am not entirely sure what's going on here. I look at it, it doesn't look like Quicksilver actually makes contact with him. I'm assuming that he just splashes some of the water from the water sprinkler into the guy's face and knocks him over with the water droplets, which would be kind of tough as it is, because you imagine it's basically like buckshot at that point, just a bunch of masses hitting you in the face at high speed. So not so great, but we could actually delve a little bit deeper into the idea that if you agitate molecules faster, they actually increase their temperature. That's how you heat things up. So we could also imagine that as Quicksilver interacts with the water, he makes the water molecules vibrate faster and actually superheats it a little bit. So not only could you get like buckshot of water molecules into your face, they could be superheated with some 3rd-degree burns as a little bonus there. All right, I think this one's pretty straightforward. Poor Agent Dennis has a dinner plate thrown at his neck at supersonic speed. I feel, I'm pretty sure he's going to be just straight out decapitated by that. So sorry, Agent Dennis. Oh, Agent Edgar, he has a rough, he's got a rough one here too. All right, Agent Edgar, gun knocked out of his hand, and then Quicksilver goes and lifts him up by the back of his pants into the air. All right, let's see here. So first of all, if you notice, Agent Edgar is like sort of holding the gun, and then Quicksilver just kind of magically lifts it out of his hands. But there is a trigger finger there. So I'm going to argue that Quicksilver moves it out of the way so quickly that he basically amputates the guy's trigger finger, because he certainly doesn't have time to open his hand, and the gun moves. So Agent Edgar is -1 trigger finger there. He's, I mean, he gets a wedgie of wedgies. I mean, that is, yeah. I'm just gonna, sorry Edgar, that's bad news for you there. And then the fact is, he's actually lifted into the air by the impact. And as we said, as the movie shows for other parts, once objects start moving, they keep moving. So I'm gonna just go with the idea that he was thrown up with enough force that he's probably gonna slam up into the ceiling, realistically speaking. So Edgar had a bad roll of the dice on this one, man. Sorry Edgar. Okay, next up is Frank. Frank's gun is also removed from his hand. Then Quicksilver takes the time to close the guy's fingers into a fist and punches him with his own fist. Oh, all right. So again, we have another situation where the guy literally has the gun in his hand and Quicksilver just rips the gun out. So I'm going to say another missing trigger finger here. No part of Frank's body is designed to move as quickly as Quicksilver is moving it. So I'm arguing that Quicksilver shatters like a lot of bones in the guy's hand, moving them as quickly as he does, moving his arm as quickly as he does. He shatters a bunch of bones, and then he slams it into the guy's face. Just bone breakage everywhere. and then a massive impact into his face from his hand, which I assume is going to cause all kinds of damage to his face, and also throw his head backward violently as well. So Frank had a tough one there too. All right, then I don't know if Quicksilver is getting bored by this point in the fight, but he starts to get a little more creative here. Agents Greg and Howard are standing next to each other. So this is sort of like a Frank plus scenario, I'm going to argue. It ends up in a similar way, but he does a little bit more there. He drops their outer arms, and then he takes each of their inner arms and crosses them over each other such that they're hitting the other person in the face. So when he pulls their arms downward, I'm assuming he's just going to straight out just rip the shoulders out of the socket, I would say at that point. Plus wherever he's grabbing onto the arms, I'm sure he's breaking the bones there. And then we have a Frank scenario where you're getting punched in the face by a fist, but it's the other person's fist. So I don't know, a little bit of fresh take on things. So Greg and Howard, probably a little worse off than Frank, I would say. Okay, so there we go. Let's bring this home. While Quicksilver's interactions during the clip seem to be very gentle and very measured, Quicksilver seems to be going out of his way to just do the bare minimum to take the guards out. And while I can applaud his control there, in the real world, you cannot be gentle with something if you are dramatically changing its motion in fractions of a millisecond. Golf clubs and baseball bats. If you watch any of the slow-mo clips of those interactions, it may look very soft and gentle as the thing is folding out at very, very slow speed, but play it at regular speed, and those are violent, sudden interactions. So I think really what it comes down to is that if you're going to notably change the motion of a massive object in a fraction of a millisecond, as Quicksilver does, he must supply massive forces. And the calculations that we made earlier in the video was Quicksilver moving a 10-gram bullet. He also seems equally capable of moving much larger hands and arms, even lifting a guy up off the ground by his belt. So he is providing much greater forces as the mass increases as well, and he's still able to accelerate objects that quickly. And as a mutant, he might be able to endure the stresses associated with acceleration at that really high speed. But the rest of us normal humans do not enjoy any such immunity to damage in that scenario. So I'm going to make the call that any guard that is actually subject to the forces from Quicksilver would experience significant, debilitating, and perhaps lethal injuries. And you know what? I still think it's a fun scene. It doesn't have to be a perfect scene to be a great scene. Yeah, I honestly would rather see the guards all knocked out than experience whatever horrific injuries would actually occur during that scenario. And again, I still think it's a great scene. I am not even upset that I discovered in the process of doing this video analysis that Quicksilver, again, interacts with 8 guards. But when they do the overhead shot, take a look. There are 3 more guards that he took out that they didn't even have time to show us about in the movie. So what do you know? Maybe a director's cut is coming somewhere. Who's to say? But again, great clip from a good movie, and I appreciate you being around to help me analyze it. And as always, thank you for watching Action Physics from the Transparent Physics channel. Hey, I love talking about physics, and I love talking about superheroes, so it's a great combination. If you enjoy it as well, feel free to leave a like on the video. If you have any questions about what I said or how I said it, leave it in the comment field below. And to find out what's coming next from Transparent Physics, I always greatly appreciate the subscribers.
Thanks, kid.